Hey guys, so we are going to be looking at finding centroids today, another review from statics. So remember, a centroid is where you could balance something on your finger. So like if I had this eraser right here and I wanted to like balance it underneath on my finger, like it's easier to do it across the whole axis than to find that sweet spot where the whole thing balances. But that's what we're going to be doing with centroids. So if I have a rectangle or a square, and remember you guys got these sheets last year. These will also be in your strengths modules so that you can print these off again. Additionally, for all these modules you're working now, I have cut and pasted the shapes that you'll need, just so you don't have to print anything off yet. So if we look at a rectangle or a square, we're given the area. We're giving moment of inertia about the x-axis and moment of inertia about the y-axis. We can also see that the centroid it's halfway between up and down and halfway between right and left. Okay. For a circle, we have the same idea. We have an area. R is given as the radius, moment of inertia. For a semicircle, again, here's the center. It's 4r over 3 pi up from this x-axis. And this is a great one to look at. So let's look at this x and x prime. X is a global axis. It's usually either an axis that's given or it's known, or in this case, it's just the bottom of this half circle. Okay. X prime is always going to be the axis that goes through the centroid of the shape. So if we look up here at this quarter circle, X and Y just define where we cut that piece of pie out. X prime and Y prime define where the centroid is within that shape. So if I were to look at just this 6x6 box, you guys all know that the center would be here, and it would be 3 up, and it would be 3 over, or I could say it's 3 over this way and it's 3 down. It doesn't matter where I want to put the axis. I just need to be consistent that it's coming from the outside edge of that square. Okay, so this would be my x prime, and we could call this, if we wanted to, x, because we marched up halfway to get to the centroid. So this is our global. This is our local. We also call this centroidal. And I might call this y bar, like find y bar. Find y bar to find the local or centroidal axis. Global is going to be where we take that y bar from. Okay, this direction is x bar, and x bar gets us from the y-axis to the y prime, which would be the local or centroidal. So now let's put that square on an xy system that looks like this, and we'll still use our 6x6, but we're off from the y-axis by 2, resting on the x-axis. So if I want to know where the centroid is, coming from my global x-axis, I'm going to march up. The math is easy to do. 6 divided by 2. Okay. If I'm coming from my global y-axis, then the centroid is actually going to be located at 2 plus 3, which is 5, because I'm having to march 1, 2, 3, 4, 5 over to get to where that centroid is located. So again, this would get us our x prime and our y prime. So what if we have something that's a shape, and we can just do something like this? We'll still use our 6x6, R2, and then let's say that this is 6 tall. So it's a 6x6 triangle. So I don't know if you guys remember, the equation for y bar is the sum of a's times their own centroidal distance from the global divided by the sum of a's. And we usually make a chart. And so we know we need an area, we need a y, and this y is from my global to the centroid, from my global to the centroid of each individual shape. And then we'll call this a times y. just to eliminate lots of math. So we're going to look at shape 1. What is the area of shape 1? It is 6 times 6. And I always in my head say base times height. Okay. Y. Y is from my global to the centroid of the single shape I'm looking for. So that distance is going to be 6 divided by 2, which is 3. So we get 36 times 3, and I get 108. I'm calling up positive. If I'd had to go down, this y would have been negative, but we're moving upwards. Okay, so now I need to look at the area of a triangle. So that's going to be 1/2 base times height. So we get 18. And this time I'm going to start at x and I'm going to march up 6 because I have to get up 6 just to get to the base of that triangle, plus 6 over 3, because in this case it's going to be a third of the way up from that base. Okay, so that's going to be 8. So now I have 18 times 8, so I get 144. So even though this area is quite a, it's half the size, it's got a much larger a times y because its centroid is located so much farther away from that x-axis. So I need to sum my areas and my a's times y. So I have 36 plus 18, and I get 54. 108 plus 144, I get 252, and y bar equals ay over a. So I get 252 divided by 54, and I get 4.67, whatever my units are. Now, this is the important part. You guys all want to grow up and be engineers, and a big chunk of engineering is not just coming up with an answer and calling it a day, but it's going back and asking questions. Does this make sense? When you start a centroid problem, my suggestion would be to go ahead and look at that. Okay, I know the whole thing is 12. If these were both squares or rectangles or whatever, then I know that centroid would be right up here at 6. Does that make sense? Okay. So if I cut off part of this area, I cut it all off, I made this area smaller, that's probably going to shift that centroid down some because I have more area down here. Remember, we're finding that sweet spot where we can stick the shape on our finger, lay it on our finger, and we can balance it. And so it's usually going to be, like in this case, where there's more area. Now, my expectation would be it wouldn't be at 6 units, 6 inches, 6 feet, 6 millimeters, and it's not going to be at 3 because it would be at 3 if I didn't have that triangle on top. So my guess is it's somewhere going to be between 3 and 6. Okay, and 4.67 seems like a reasonable number. If I had gotten 14 here, 14.67, don't turn in that kind of nonsense. 14 isn't even within my system. It can't be 14.67. This is where I would really say at this point in your engineering career, you really start thinking about the answer you got and asking yourself, does this make sense? Okay, so let's look at going from the y-axis. So y bar is 4.67. That's my units up. So if I wanted to call the coordinate of this, well, I'm at 4.67 up. Okay, how far over am I? I still need to get that over part. Okay, look at this. It's symmetric. Both of these centroids are going to lie on this internal axis, which is going to be 3 over. I can look at this and know that this centroid ought to be 2 plus 3, which is 5. So y prime, my x bar, should equal 5. Okay, let's just set it up and see. So I need area, I need a y, and I need a y. Area is still 36. Base times height, 6 times 6 is 36. Y. Y is now going to go 2 plus, because I have to walk from that global axis, I have to walk over 2 just to get to the rectangle so that I can continue to walk my 3. Okay? And then we have 36 times 5, which is 180, okay? And area of my triangle hasn't changed, it's 18. And to get to the centroid of this triangle, I have to walk over 2 just to get to the edge, and then walk over 3. 18 times 5 is 90, okay? So now I can add, we still have 54, that's still my area, and this should be 270, and 270 divided by 54 is 5. So that equals my X bar. And that's kind of what I guessed it was based on symmetry. So if I'm looking at where that centroid is, it is at 5, 4.67. That's where the location of it would be if this were graphed out, or if I had plans, maybe these were construction plans and I needed to know right where that centroid was for machining, or any sorts of things, okay? If you have a negative area, so if I have that same box, and I cut an area out, then the area is going to be a negative value, okay? Now, if I walk up and I walk up, my distances y can be the same, and these are both positive, but I need to make sure that the area of that void is what I'm cutting out.